field models.
Thanks, Anya, and thanks for the invitation. And I hope my audience in Europe and Asia are not too tired by now. Okay, so the talk you just heard, the last two were in fact the perfect introduction to what I'm going to be talking about. Okay, so I'm going to be talking about bumps of activity in neural fields. Now here are a few references just to see where this is coming from. I've got an archive preprint up the top that goes through the theory in this talk in much more detail. I've also benefited from Bart Freckelberg, Paul Bresloff, and James Inglis. You can look up the papers there if you're interested. Okay, so first I'm just going to outline a general formalism. Okay, so in general, I'm interested in spatially extended equations. This could be a partial differential equation, it could be a neural field, and such that we have added noise. And I want to understand how the noise is going to shape interesting dynamics over long periods of time. In particular, I'm going to assume that there's a smooth manifold of fixed points to the deterministic equations without noise. Okay, so I'm parameterizing this manifold by phi of alpha. Now, there's a good motivation for this because very often in these equations, there'll be some sort of pattern, such as a bump, which Bastian was talking about. And this pattern will be invariant under some sort of isometry. Okay, so that could be a translation of the bump. So you can translate it left or right, and that will still be a solution. Or it could be a rotation if it's a spiral wave or some sort of phenomenon like that. And my basic question is, if this manifold of solutions is attracting, how is the noise going to shape the dynamics in the neighborhood of this manifold over really long periods of time? Okay, so I'm looking at the metastability of this manifold of solutions over really long periods of time. Okay, so I think the last two talks were a great introduction, but just to repeat, I'm looking at spatially extended noise. Okay, so what that means is if you take any particular spatial point, X, the noise at that point is just a Brownian motion. Okay, so it's white noise with increments that are independent of the past history and with variance t minus s. And if you take any 2 points, then the noise processes at those 2 points are going to be correlated according to some function q of x, y. Now, I'm going to look at neural field equations, and in neural field equations, we do need some spatial correlation, otherwise we can't make sense of the solution, okay, because you don't get a continuous solution if you don't have some correlation in the noise. There's a good motivation for this noise, and talks at this conference did that for me. So yesterday we had Guilherme Ost talking about deriving a neural field model from a network model. And today we had Bastian Petras also talking about that. In both cases, if you take a neural network model and then you do some sort of coarse graining where you take averages, then if your finite size network model is noisy, then that cumulative microscopic noise is going to scale up and lead to noise at the macroscopic level. And typically the magnitude of that noise will scale as the inverse of the system size to the power of a half. Okay, so this is just the central limit theorem. Another way you can have noise is you can have anomalous inputs coming from other areas of the brain as well. So in particular, if we're talking about correlated noise, then generally, if there is correlated noise, you expect that to be due to correlated inputs rather than these finite size effects. In any case, you can always represent the noise just by taking a spectral decomposition, which I've got at the bottom. So you can write it as just an infinite sum of independent Brownian motions multiplying by some correlation function, ejx, and then some magnitude, lambda j. I have to assume these magnitudes are not too big as j goes to infinity. Okay, so where do I want to apply this theory? Well, I'm interested in the visual cortex, just as this is very similar to what Bastian Petras was talking about. So this goes back to Hubel and Wiesel. So we have neurons that are preferentially excited by inputs of particular orientations. Okay, so an orientation is between minus 90 degrees and plus 90 degrees. And each neuron is going to prefer one of these orientations, and it's going to be preferentially connected to other neurons with a similar orientation. Okay, and what we find is that you can get a bump of activity that will be a stable attracting state of this system. So the idea is a particular orientation strength will be more excited, and that will excite its neighbors to a lesser degree because of the recurrent connections. And so if you see on the left, you get this bump of preferred orientations. What I want to understand is, how does this bump of activity evolve over really long time scales? In particular, can I make predictions about where the bump of activity would be just by looking at the correlation structure of noise and how that interacts with the manifold? Okay, so here's my neural field equation. It's just, so the spatial variable, theta, so-called, is just the orientation. Now, to make life easy, I'm saying it's between minus pi and pi, just so I can parameterize it by the ring. I'm taking basically the same model as Kilpatrick and Ermentrout. Okay, so they proved that you have, if you take J to be the Coles function, then you get a bump solution, a manifold of bump solutions, because you can always take one solution and translate it in either direction, you get another bump solution. And it's locally stable, and they've got a very nice analysis where they can easily pick up every single eigenmode and its eigenvalue. So it analyzes really beautifully. Okay, so I want to add some white noise to this and understand how does my bump activity shift over long periods of time. Okay, this is stuff I've talked about before, so I'm going fairly quickly. Now, if you look in the bottom left, this is the sort of profile you'd get if you did a stochastic simulation. Okay, so you can easily discern the bump. You can see there's noise, it's not homogeneous, and the noise is going to cause the bump to drift in different directions over long periods of time. So earlier analysis by Kilpatrick and Ermentrout and Paul Bresloff have picked up the leading order diffusive flux of the stochastic shift of this bump induced by the noise. Okay, so that works over timescales, relatively short timescales. And what I'd like to do is go to longer timescales. Okay, so over short timescales, it just diffuses left and right. But if we take really, really long timescales, it's no longer just going to be governed by diffusion. I want to try to predict where the bump is going to go. Okay, so to do this, I need a sensible definition of the phase, okay, because we have an infinite dimensional stochastic differential equation. You can't analyze that analytically just off the bat. We need to reduce this to a one-dimensional equation by taking a phase map. Okay, so this map that I developed with James Inglis and Paul Bresloff, which we call the variational phase map, is to say, well, let's define the phase to be such that the difference of our solution U to the point on the manifold, which is parameterized by phi of U, okay, has to be, we want that to be perpendicular to the eigenmode of the adjoint of the linearization. So this sounds like a bit of a mouthful, but all this is really saying is choose the nearest point on the manifold to be such that there's a linear decay of the amplitude vector. Okay, because we're saying let's choose the phase that will ensure that this amplitude is going to decay as quickly as possible if there wasn't any noise. So it's just saying basically choose the coordinate system in the right way that we have this amplitude vector decaying. So this is a useful definition in many ways. I've talked about this before. You can always define this once you're close enough to the manifold. Now, I should be clear here, we are assuming that there's only one eigenvalue of 0. Okay, so that's in directions tangential to the manifold of bumps. Okay, we know there has to be an eigenvalue of 0 because if you translate the bump, you still get a solution. So that basically means when you take a derivative that there has to be an eigenvalue of 0. But we're going to assume every other eigenvalue is negative, so that every other eigenmode is decaying in. Okay, so you can use this analysis in Kilpatrick and Ermentrout really nicely and adapt it to our setting and get some really nice bounds. Okay, so it turns out if I take this definition, I can then define a stochastic differential equation for the phase, which I'm calling B to T. And this satisfies, we get an exact stochastic differential equation, which will depend both on the phase and on the solution, U of T. Okay, so this tells exactly how this phase is going to drift stochastically over long periods of time. Now, it's impossible, in fact, that this will be valid for all time, because what happens is that there's always a chance of a large stochastic fluctuation. And it's possible, in theory, that this fluctuation could mean that you can no longer uniquely define this phase. Okay, so basically what happens is, this is basically a failure of the implicit function theorem. Okay, because if you go to my previous slide again, I'm solving this using the implicit function theorem. So if the derivative of this with respect to phase is 0, then the implicit function theorem fails and I can't solve for it. Okay, so it's actually not surprising that there's a possibility this will fail. But what we want to do is prove that this is very unlikely over long periods of time, prove that this phase description is very accurate. Okay, so we've derived exit time estimates. Okay, so we define our amplitude. Okay, and one of the benefits of using this definition is when you write out the SDE for the amplitude. Okay, so this is the difference between the solution and the nearest point on the manifold. What you find really nicely is that this is dominated to leading order by the linear decay due to the linearization. Okay, remember I told you that every eigenvalue is 0 except for the directions tangential to the manifold. So because of that, the way this is defined, the 0 eigenvalue of this linearization won't affect V, because V is by definition orthogonal to that. So that means we get a uniform decay here, which will dominate higher order terms in the drift. Okay, so this is basically now a stochastic escape problem where you have a well with a typical decay towards the bottom, you have stochastic fluctuations, and you can basically find a theorem that says that the probability of this exceeding some threshold is really small, is exponential in the magnitude of the noise epsilon and the size of the fluctuation A. Okay, so we expect it to drift for really long periods of time next to the manifold. Now we're going to ask ourselves, well, where do we typically expect it to be over these long periods of time? And as a follow-up, do we expect oscillations? Okay, because we do have a periodic manifold. It's S1, it's the ring. Is it the case that the noise could, just through correlations, induce slow oscillations in this system over really long periods of time? My answer to that is going to be yes. Okay, now a problem so far is that we haven't quite completely separated the phase from the amplitude, and this is going to lead to problems with the analysis. Okay, because at the moment, if you just do a linear order analysis of our drift in our SDE, we get an epsilon squared term, which is okay because that's small, but we have a norm of VT squared term here, so not B is the amplitude. The trouble with this is that we know that typically values of this amplitude are order epsilon, okay? Because we know the amplitude typically is at the situation where fluctuations from the noise, which are order epsilon over small time scales, get brought back down by the natural decay of the linear stability. So what that means is that typically this amplitude term contributes roughly the same amount to the drift as these other terms. It's roughly order epsilon squared. So the basic problem is we have not separated the amplitudes from the phase as much as we would like, because amplitude fluctuations are still affecting our phase analysis. So what we need to do is define a better phase for this purpose, which I'm calling gamma t, such that the drift is purely to leading order epsilon squared. It's not going to leading order depend on the amplitude. Okay. Okay, so those of you who work in oscillators would probably tell me immediately what I should have done, and that's to define the isochronal phase. I've called it the isochronal phase because that's what it's called in oscillators. This is just basically the phase where the system would go to as t goes to infinity if there wasn't any noise. Okay, so it's the mapping from a neighborhood of the manifold to a phase, which is in S1, such that this is the point of the manifold it would go to as t goes to infinity without noise. This is useful because what happens is just because of this definition, under the deterministic flow, the isochronal phase must be invariant. Okay, so this gives us this nice property I'm showing here. The gradient of the Freshet derivative of my isochronal phase map, multiplying by the dynamics for the deterministic flow, has to be 0. Okay, now you can show easily that this definition is very close to my other one, and they only differ by the order of the amplitude squared. Okay, so it's not a big difference. But the big benefit is when I use Ito's limit to do my change of variable formula, suddenly I get rid of that term which was causing me problems in the previous 2 slides. Okay, so in the previous 2 slides I showed you I had this order norm of VT squared, which is of order epsilon squared. Okay, and that was not allowing me to separate the phase from the dynamics. Now it turns out you no longer have that. You have an order epsilon squared term here. Okay, now it is still depending on the solution U, but because everything's nicely behaved, I can approximate U here just by its nearest point on the manifold, phi of gamma tilde S. So this second equation here, which hopefully looks like a good approximation, because I'm just replacing U by its value on the manifold, which we know is small as long as our previous probability bound holds. So the benefit here is now we suddenly have an SDE that is self-contained in the phase. There's no amplitude here, there's no U. And this is in effect, it's driven by infinite dimensional noise. in effect, it's a one-dimensional SDE because every term here only depends on the phase. Okay, so we can use one-dimensional SDE theory on a ring to solve this and get some nice results. Now, one way to help see this better is, in fact, it's more instructive to do a rescaling of time. So if I take this equation and I rescale time, okay, so I say t goes to epsilon squared t here. I'm defining this new, this is bad choice notation, this is epsilon, the Greek letter here, it's not v. So if I do this rescaling of time, I get rid of the epsilon squareds here. Okay, so the rescaling of time, it only affects, you take the square root of the rescaling to come in here, the coefficient of noise. So this is even better now because this is an SDE, it's one-dimensional, and it doesn't depend on epsilon. Okay, so we're hoping that this SDE here is going to tell us a lot about how the phase wanders over long periods of time. Okay, so I can derive the invariant distribution for this SDE for epsilon. Okay, this is just one-dimensional calculus now. I take my diffusivity, I take my drift. Now I haven't written it out, but I have a perturbative, leading order perturbative expansion of the second derivative of my isochronal phase map. It's in my paper, you can look it up if you'd like that. It's just involving inner products and various things. So I can solve that analytically for my case. I need this diffusivity to be greater than 0, so we don't get anything pathological going on. Okay, so I get a Fokker-Planck equation for the law of my one-dimensional SDE on the ring, epsilon t. So this is just first year calculus. Now, I know that the solution of this SDE, sorry, this PDE now, it's a PDE for the probability distribution. This is going to converge to a unique attracting probability measure. That's just because the coefficients are continuous, the domain is compact. Okay, so it's what I've got here down the bottom. It's running P star to be the invariant probability density. Now we have this nice convergence. It's going to go towards that. This is just standard theory. And we can solve for this invariant probability distribution by just setting the derivative with respect to time to 0. Okay, now this is just one-dimensional calculus. I can solve that exactly. Okay, and so what we basically find is that this is the first result. So as the bump wanders over really long periods of time, if I take any continuous function, okay, make it differentiable to, evaluate it with respect to the value of the isochronal phase at that time t, and take the average with respect to time. Okay, so this is sort of a way, so imagine g is some function that is 0 almost everywhere, and it just concentrates in some particular small interval on S1. Okay, so the value of this average would be telling me, well, roughly what proportion of time does the isochronal phase spend in that region over long periods of time. Okay, so here t is enormous, okay, with some function which depends on delta. So what this result is saying is that the average amount of time it spends in that region would be just given by the average with respect to this invariant probability distribution. Okay, so this probably makes sense to some of you because it's basically saying the long time ergodic average is just an expectation with respect to the invariant probability measure. Okay, with very high probability. Okay, because remember this is still a random variable. So there is a finite probability that this doesn't hold, but it's very small. Okay, so you can phrase this another way if you like using occupation measures. It's just saying the same thing. Okay, so now a few quick numerical examples. Let's first drive this by almost white noise. So it's white in time. It's not quite white in space, as I was saying, because if you have completely white in space, you can't make sense of the solution. So what I've done is I've taken my correlation function here to be just a summation of lots of Gaussian things with a small variance concentrated at thetas. So I've just discretized space. Okay, so it's almost white. Okay, so you can see my correlations here are very much concentrated on the band and drop to 0 quickly. Okay, and unsurprisingly, you find that the invariant measure here is just uniform. It doesn't really want to go anywhere. It's just as likely to be anywhere else over long periods of time because the noise is not encouraging it in any particular direction. So now let's take a different noise. Let's take a large spatial correlation. So just to be clear, I'm always going to have a bit of white noise, okay? Because I need my diffusivity to not be 0 or I can't solve everything. So I have a small amount of white noise. I'm adding on a big spatially correlated noise here. Okay, this could be from anomalous inputs from other areas of the brain, for example. So here, there's one extra noise source. it's spatially extended. It's inducing correlations. It's only positive correlations. And what we find is that immediately the phase wants to concentrate in some places, so roughly -2 or +2, and it doesn't want to be at 0 or at pi. Okay, so immediately the noise is preferentially sending the bump in particular directions. So here, this is my drift function here. This is my diffusivity. Okay, so that's one example. So immediately we're seeing the noise encouraging the drifting of the isochronic phase to particular areas over long periods of time. Okay, here's another example. We have, now I'm taking spatially extended anti-correlation. Okay, so again, I'm taking just white noise as a base, and then I'm adding on a single dimensional noise here spanned by Q bar. This is now I'm taking a normal distribution, mean 0, some variance. I'm multiplying it by x. Okay, so normal distribution is symmetric about the axis. I'm multiplying by x to make it anti-symmetric. Whereas I'm doing this, is make it anti-symmetric means you get anti-correlations. You can see here the strong positive correlations on the diagonal, and we get anti-correlation here. So that means that if neurons at particular, if neurons at particular values are likely, if the fluctuations are likely to be positive somewhere, they're going to be with high probability negative in other parts. So you have an anti-correlation structure to the noise. And